Good morning, everyone. You have made it through quite a lot of the clinical biomarkers work. We've talked about proteomics as a way to discover biomarkers, ELISAs and other immunoassays as ways to quantify proteins, specifically from biofluids. We've talked about gene expression biomarkers. I think Byron did a really great job, Dr. Reeve did a really great job with that on Tuesday. Today, we're going to start talking about how to deal with the data from biomarkers, though. And I'm going to spend the entire lecture around this concept of receiver operating characteristic curves. That term feels a little unwieldy, and so most people talk about these as ROC curves or ROC analysis. So when you hear that term in connection with biomarkers, I always want you to be able to understand how to interpret those data. So today, we're going to spend our time with that topic. I can't really reach it from there. Okay, so we will be starting with this definition of a classifier. A decision rule or a classification engine. These are many different terms that get applied, but in each case we're talking about binary classifiers that make a decision about this person is in this group or in that group. This person does have early TB, this person does not have early TB, for example. So these binary decision rules are something that we need to start with, and we're going to remind everybody of the definitions behind sensitivity and specificity. Everyone should have a really clear grasp of those two concepts, I think. From there, we're going to talk about working from experimental data and translating this into a table of scores that we can then use to assign labels to study participants. So we'll draw and characterize an ROC curve that's derived from these tables and try to explain how one relates to the other, what looks like a good curve or a bad curve from these data. And we will, of course, talk about how to set a cut point. Have people heard the term cut point? If I were going to my doctor, one of the things that my doctor might do is have me stand on a scale, right? Okay, so I take my shoes off because they're certainly going to add to my weight. I'm just standing on the scale for a moment, and then the weight comes back and it says, you're 80 kilos, 80 kilos. So, is that good or bad? What's that? Little worried? On a scale of 10, I'm going to die tomorrow from heart failure, to 1, oh my goodness, I need to shove a beef sandwich in me right away. Where do we sit? 80 kilos? What? 3 or 4. Okay, so I'm not yet in a danger zone. People aren't going to say, just what day are you planning on developing diabetes yet? But what if I walked in there at a weight of, a mass of 100 kilos? Kind of high. Kind of high. All right, so I'm relatively short, right? So, I mean, if I were a 7 footer, if I were above 2 meters in height, and I weighed 100 kilos, that might be totally expected. I might be a really beefy person who was a brilliant athlete and so on. But someone at my height who's 100 kilos is not likely to be great in athletics, right? So we have to have some way to contextualize that result. So being able to think about cut points is to say at what stage is this measurement problematic or not, right? So that is a cut point. So we're going to talk about ways that, oh goodness, I really can't reach that keyboard from there. There we go. So we're going to spend all of today really talking about what makes a metric a good one or not on the basis of an ROC analysis, and how do we make a decision that represents a cut point for that metric. Okay, so let's start with a binary classifier. You've probably heard the term binary in connection with computers, right? It's someone who says, computers only know 1 and 0, blah, 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 and then say something unfounded from it. However, binary largely means 2 options. Okay, so a digital circuit may have current flowing through it or not having current flowing through it, and that's what makes it a binary circuit. But in this case, we're talking about a binary classifier. So I want you to think of our subjects here as being individuals on whom we need to make a decision. And up here, the person in the hat sitting at the table is a judge. So this judge is going to say, you are class A, you are class B, you are A, you are A, you're B, you're B, etc. This judgment, this decision, is a binary classification. Now, because we're only allowing for 2 categories, you're in cases or you're in controls, you're in the 6 or you're in the not 6, we have a binary decision. It is possible to make something called a ternary classifier, which has 3 categories. Maybe you're definitely sick, you're in the danger zone, and you're completely fine. You could make decisions like that. But generally speaking, when we do ROC analysis, it's built around this concept of a binary classification, 2 categories. So we have a heterogeneous group of subjects, and we want to cut them to 2 different classes. Generally speaking, we work on some sort of score. So if you were trying to pick who's going to be on your basketball team, you might say, well, tall people probably play basketball better than short people. That is a very arguable thing, right? I mean, point guards aren't particularly tall, but they can shoot from way, way back. Tall people, on the other hand, are much more likely to dunk than someone would say my height, right? So if you're looking at these folks on this basis, you might simply represent each person by some metric, height in centimeters, for example. And then you can say, if somebody is above 2 meters, then they can be on my basketball team. And if they're below 2 meters, no, I'm not going to take them on my basketball team. All right, so you could do something like that. So this would give you a way to represent each case or control, each person in your sample by a value that you use to make a decision about them. This is the crux of how we make decisions clinically in this case. You will sometimes see this called a dichotomous classifier. Dichotomy means that you have multiple states, a pair of states, and dichotomous means you're cutting into these 2 classes. All right, so everyone gets the idea of binary classifier? Right, all right, next slide. Okay. Now, I grew up Southern Baptist, which is kind of an interesting church in the Midwest of the United States, and as a result, I can hardly think of binary classifiers without thinking of paintings of the Last Judgment. If you didn't get this in Sunday school, the short version is that we have some sort of metric that's being used to evaluate people at the Last Judgment. Some of them have hearts that are pure and clean, and they pass into paradise. Other people have hearts that are weighed down by awfulness, and they pass into hell. All right. Does that constitute swearing? I'm not sure. Okay. You're going to let me pass that one. Thank you. All right. So this is the Last Judgment is an example of a binary classifier. Here we see the metric of generation. This is a pair of scales that the angel is holding here, and the decision rule is the judgment based on the performance of that scale, whether this person goes to heaven or into perdition. All right. So I hope that's a useful metaphor for you to think about what these clinical classifiers are attempting to do. Plus, it's just kind of an awesome painting. It's kind of metal, if you ask me. All right. Now, how do you start creating a classifier? The ROC analysis is an attempt to evaluate how well a particular decision rule or a particular metric is performing for separating patients into 2 classes. So we're going to start with this set of patients. We have 10 of them. You see, patient A, patient B, patient C, up through patient J. Each of them has some sort of score. Now, we've talked about a lot of ways to get that score. Maybe these are PSA tests, right? So maybe we're testing for the amount of prostate-specific antigen circulating in their blood, and that's the score right there. But we also, in this case, just in this case, know the label for all the people in the study, right? So we know that these 5 people are positive for prostate cancer, and these 5 are negative for prostate cancer. Now that could be for tuberculosis, it could be for whatever condition you want. But in this case, we have a truth column that's giving us a plus for all the cases and a minus for all the controls. So just because they're sorted in the order A through J is just the order in which they were registered for the study. So we have our knowledge of whether this person really does have the disease or not, and we have some number that attempts to capture on the basis of some particular biomarker what their score would be under this scoring system. Everyone good so far? All right, so 10 people in the study, we've got a known label for them, and we have some measurement for them. In the second case, we're reordering all the patients. You see that? We started with A through J, now they run patient D, then H, then I, then C, etc. So how did the ordering change? The only change is that we've said the higher the number, the closer to the top I want them to be. The lower the number, the metric that we've measured for them, the biomarker measurement, the lower they're going to be here. Now I want you to notice something. As we sorted on the basis of score rather than registration letter, something happened to our truth column. Did you see that? So before, patient D was called a plus, and they're still called a plus. That hasn't changed. We're just changing the ordering of the patients to match that of scores. So we still have 5 positives here and we still have negatives here. But in the first case, they were all mixed up, right? It went minus, 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 plus, 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 minus, plus, plus, minus. Very strange ordering there, right? There's no apparent rhyme or reason to it. But when we sort on the basis of this score, we suddenly have these long runs of pluses and long runs of minuses. The pluses tend to be at the top. The minuses tend to be at the bottom. But are they perfectly separated? They're not. This is the nature of the beast. Anytime you're going to do a clinical biomarker, that clinical measurement is going to help you separate the pluses from the minuses, but it's not going to be a perfectly clean separation. This is the fact of the matter, and we have to have some way of characterizing how well this metric separates the cases from the controls in this case. Okay, so we started with our observations of all the patients in order. We reordered the patients based on that metric. And finally, we're going to need to find some decision rule on the basis of that. Now, you might say, well, the score seems to run from 0 to 1. So maybe the best place to throw in a threshold is 0.5, right? And it might be that the type of analysis you use to create that number makes that an automatic assumption. Maybe you'd use logistic regression, for example. But in this case, if you knew absolutely nothing about the source of this number, you might say, well, I'm going to set my cut point at 0.5. And if you look above 0.5 in score, you have a perfect result, right? Everything above that score is actually a positive. And the rule of higher than 0.5 is positive gives us a perfect match with that. But look below 0.5. If you set your threshold at 0.5, you have 2 more positives who are below that threshold. So that's problematic. We need to find a rule that reflects the true the truth levels that we have for these. And we see that if we were to set our threshold at 0.5 here, we would be in real trouble because we would be losing 40% of our positives. Okay, so in this case, we can set the rule to be, say, 0.4. Now, all of the positives are above it, but there's a cost to that. By setting our rule at 0.4, we now have ruled positive somebody who's actually a negative. We know that by ground truth, that person is a negative. So there's no one place where we can set this threshold that's going to give us perfect separation. And we have to figure out where to set it in order to maximize our accuracy, essentially, for that rule. Everyone good so far? Okay. But there's no curve here, right? So we need to talk about how these data become a curve. Oh, but we're going to take one stop here. This is probably stuff you remember from other classes, but in particular, it's important that you understand sensitivity and specificity. So for this, we're going to compare 2 classifications. One is reality. In the case of constructing an ROC curve, we know the labels, the true labels for everybody. We know that this person does have cancer. This person does not have cancer. My goodness, that should have shut on. Okay. So we know that 5 of the people in our data set do have the disease, and we know that 5 of them don't have the disease. But we also have a judgment we've made on the basis of some rule. Given this threshold, we would say that these people are positives, and yet one of them was a negative. We would say that the people below this line are all negatives. That's correct. So in this case, it may be that somebody does have the disease, and our classifier says, oh yes, they do have the disease. Our rule on how to interpret the metric says that they do. That's called a true positive. Everyone has that? Great. It's also possible to evaluate on the basis of true negatives, which is to say, we know in reality that person doesn't have the disease, and our software also says they don't have the disease. Those are true negatives. But there's still this opportunity for us to have made an error in each of the two directions. In the one case, somebody really is sick, but our rule misjudges and says they don't have the disease. This is called a false negative. Somebody is truly positive, but we've mistakenly ruled that they don't have the disease. It's also possible to make the error in the other direction. It may be that somebody doesn't have the disease, but our rule says that they do. This is another mistake. This is a false positive. So there are kind of 5 different metrics that fall out of this very easily. Positive predictive value, negative predictive value, accuracy. Did you know accuracy has a statistical expression? It does. It's the number of true positives plus the number of true negatives divided by the total. Easy to get to. That's fine. But the ones I really, really want to make sure everybody gets are sensitivity and specificity. So in sensitivity, we're going to ask what fraction the true positives are of the true positives plus the false negatives. So there's another way to think about this. Sensitivity is about people who really do have the disease. So ideally, your decision rule should say of all of the people who truly do have the disease, that they are sick. Everyone sees that? So if you have a sensitivity of 80%, 0.8, that's saying that your rule is able to label 80% of people who really are sick as being sick. Straightforward? That's the interpretation of this math. So the true positives plus the false negatives are all of the people who are really sick, and you're asking what fraction of them are called sick. Okay, specificity works in quite the opposite direction. So here, we're adding together the false positives and the true negatives, which is to say, all the people who aren't sick. And we're asking what fraction of them does our software call sick? So where sensitivity is asking, of the sick people, what fraction did we call sick? Specificity is asking, of the people who are not sick, how many did our software correctly say are not sick? So sensitivity and specificity are talking about different people within your study. Sensitivity only cares about the people who really are sick. Specificity cares only about the people who aren't sick. Okay. In the same way, positive predictive value and negative predictive value work off of the rows rather than the columns of this table. But I hope that that's a useful start. So in the case of the positive predictive value, we would be asking essentially, if your test says someone is sick, how probable is it? Out of all the people that your test calls sick, what fraction really are sick? You see how that works? So those are built off of the rows, whereas sensitivity and specificity are built off of the columns. Okay. All right, now I said curves were going to show up at some point, right? Okay, so this repeated from just a couple slides ago. You remember that we had 10 patients. We had a truth table where we could say, we know that these persons are sick, those persons are not sick, but what does our test say? So this is what our test says. So in this case, we're going to ignore the threshold, right? We're just going to ask, how well does this set of numbers for these patients separate them into those who really are sick and those who really aren't? So we're going to start at the top of the table, and we're also going to start down here at the origin. Now, back when I was in high school and stuff, we had, actually elementary school, one of the first ways that they taught programming was through this language called Logo. I don't know if anyone here has heard of that at this point. But I'll just tell you this, the Logo language was all about drawing using a little turtle. And the turtle could understand a lot of simple commands like pen up or pen down. And then you could tell the turtle to move forward so many paces, to turn right, to move forward, stuff like that. It was a lot of fun. It's a nice way to teach kids to program. So I want you to imagine that we have a turtle sitting right here at the origin, right, at 0, 0. In effect, we're starting at the top of the list, and every time we encounter a person who is correctly classified, every time we call someone, sorry, I've got to keep this straight in my mind. As we start with the first one, we're going to move up because our rule has claimed that someone is sick and they really are sick. So we can move up, dragging the pen with us as we go. We can continue moving up 3 times because 3 in a row, the top 3 are all correct calls. This person is sick and our software says they're sick. So we move up, up, up. However, when we hit this fourth person is not sick. So we've incurred in the fourth step of the turtle a person who is not sick. So now we need to stop moving upwards and move rightwards instead. So I want you to think about this for a moment. If our rule, if the metric we were generating put all of the pluses first and all of the minuses afterwards, then the turtle would go up, 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 and then hitting all the people who are not sick, right, 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 right. So the curve that comes out would be straight up and then across. In this case, this notch that we've cut into our curve, this step to the right, comes about because we've encountered a person with who is not in the positive category. And so we move to the right to reflect that. So essentially, these curves are going to tell us how well the pluses and minuses are segregated from each other on the basis of the metric we've computed. And so this is my little logo code. Forward 10, forward 10, forward 10 to reflect patients D, H, and I. Right 90, forward 10 means it's going to hang a curve to make this little push in right here. But then we need to turn back north again and add 2 more segments, which is how we get to the maximum height. And then we're going to turn to the right for 4 more segments in our line. So our little turtle has now taken this little path in drawing out that curve, and that is the ROC curve that corresponds to this. Now, you might say that doesn't look very curvy. I just want to point out that in this case, we have only 10 patients. So the granularity with which we can draw this curve is pretty weak. You'd really like to have something more like 100 or 200 patients if you're going to make a curve where these step sizes become much smaller compared to the rest of the curve. Okay. So as we get higher and higher, we are on our curve, as the turtle moves northward, we're getting better and better at sensitivity. Of the people who are sick, the fraction that we've accounted for already grows with each step north. X is about specificity in this case, or 1 minus specificity. So when we use different numbers of cases and controls, we no longer have this nice square space in which we're drawing our curves. There's not an equal number of positives and an equal number of negatives. Frequently we find that a lot of clinical biomarker curves have taken into account a relatively small number of cases and a relatively large number of controls. And in a case like that, you've got a lot less territory to cover heading north. So if instead of presenting these as how many truths you've captured and how many falses you've captured, it may make more sense to put these in terms of sensitivity and 1 minus specificity, because that way you're scaling for the total number of people in your study who are sick and the total number of people in your study who are not sick. Okay, right, so let us continue on to see how that translates. All right, very, very frequently when ROC curves are put into play, you will see someone expressing the nature of that curve using an AUC value, an AUC. So the AUC characterizes the ROC, isn't that great? So the AUC value represents the area under the curve. Now, did everyone here love calculus thoroughly? I mean, did it just float your boat? Was it the most amazing transformative experience of your life? Do people feel differently about calculus? Okay, well, I'm going to use a really scary word from that year then, and I'm just going to ask you to bear with me. The term is integral. Remember integrals?
Oh, triggered.
Oh, okay. I see a couple people are developing shakes out there. That happens to me too. The integral of this curve is its area under the curve. Remember that I said that in a perfect metric that puts all of the cases above all of the controls, or vice versa, either way, right? I mean, you could put the lower ones first, sort from lowest to highest rather than highest to lowest, and still get the same curve out. So you could imagine then that in a case like that, you put all of the positives above all of the negatives, and you end up with this curve that is a big right angle. So the integral of that space is 1. On the other hand, you might have a really lousy classifier. So what if I'm a big gambler, and so I try to go into medicine, and my vision is if someone's lucky, they don't have the disease, and if they're unlucky, they do. So I have them roll a pair of dice when they come into my shop, and on the basis of that, I tell, are you sick or not? Right. So is the dice roll going to be effective in separating the truly sick from the not sick? I don't advise this as a course of medicine. All right. So people come into my shop, they roll dice, and I say, you're sick. They roll it again. You're not sick. Okay. It's a bad classifier. So in a case like that, the discrimination of my test is very, very weak. And somebody being sick or not sick has no bearing whatsoever on the metric I'm generating from them. It is possible to do this even with modern biotechnology, to come up with a biomarker panel that has 0 value in discriminating trues from falses. Right? So in a case like that, you're down here in this domain, in a receiver operating characteristic curve that has an AUC value just slightly better than 0.5. 0.5 is random performance. Now, why do I say that this is the worst case? Wouldn't it be possible that I'm trying to detect people who have fever, for example, and I give all of them a thermometer, and the people who have high values, I say, are not sick, and the people who get low values, I say, are sick? That would be terrible, right? It's just the opposite of what we want. But in an ROC curve, you basically adjust your sort order such that you can separate negatives from positives, and it doesn't care very much if the negatives are on the bottom or on the top. So generally speaking, if we were to get an AUC for a curve below 0.05, we would flip the cases and then say, okay, now we're above 0.5. So this is what happens when you have 2 distributions of values for sick people and not sick people that completely overlap each other. They're basically worthless for making a clinical decision in this case. And that corresponds to an AUC value of around 0.5. It might be that you have a slight discrimination of people who are sick from people who aren't. What if, okay, so we know that a lot of diseases in South Africa have a strong relationship to poverty, right? So I could ask, how many calories does this person eat every week? And then I could use that to evaluate who does or does not have tuberculosis. Right? That's pretty sloppy medicine. But it wouldn't be the first time something that bad had been done. Right, so you could then say, I have a minor separation between the people who eat a lot of calories and the people who don't eat a lot of calories for TB. That's not a very strong separation of people who do and don't have this disease. So in that case, I might have an AUC value of like, say, 0.7 in this case. That reflects a slight correspondence between the metric and the phenomenon I'm trying to get at. Or I might have something more like this. And frankly, most of the curves that we see in successful biomarker studies have AUC values more in the neighborhood of 0.9 or something. In reality, that's very difficult to accomplish. And we frequently have a lot of things sitting between these 2 middle plots and trying to decide whether they're real discriminators or not. Okay, so although we would love to think that we have perfect discriminators in clinical biomarkers, and certainly not completely random discriminators, the truth usually falls between these two, where we have some amount of separation achievable by a clinical biomarker, but it is not perfect. This is one of the reasons why making a discriminator based on just one measurement, like just PSA for example, can be very weak, because that one molecule can only give you so much information about whether someone is sick or not. If you have 5 molecules working together, you may be able to improve sensitivity and specificity such that you start curving up away from that diagonal that represents random choices. Okay, so area under the curve is a way to summarize how well this particular rule this discriminates. This particular metric does. Okay, now this next piece is a really important thing to understand. So I've been talking about some metric that you can use for sorting the patients, right? And we characterize that using an ROC. But there's still one piece that's missing from that. Generally speaking, a clinical decision is not you have a 0.8 tuberculosis or you have a 0.6 tuberculosis. It's you do have the disease or you don't have the disease. And that's decision making, that's dichotomy, that's a binary classifier. Which means that we need to have some sort of rule that we apply for cutting on this particular metric into the people who are sick and the people who aren't sick. This is very often what needs to come out of a discriminator to give us the ability to make decisions clinically. Okay, so all 3 of these panels are the same curve. Does everyone see that? Same curve? They've all got this kind of weird vertical bit here. But the curves are the same, but the cutoff point for the 3 is completely different. We have a cutoff here where we're using a score of 8.5. Here we've got a cutoff score of 9.7. Here we have a cutoff score of 9. So how would we decide between those 3 different ways to cut on this metric to make a decision whether this person is sick or not sick? Okay, so I want to bring us back to the conversation about sensitivity and specificity, because every clinical test needs to be associated with the decision to be made, right? So let's talk about Ebola. Everyone knows about Ebola? Okay, of ways to die, Ebola is bad, right? Because you have the chance of infecting everyone you love and killing them too, right? Bad. All right, so it's an infectious disease, operates very quickly. Let's just hope it never really migrates to Paris, right? Bad things would happen then. So, if you had Ebola infection and you had a biomarker that let you decide is Ebola present or not in this person, where would you like to balance sensitivity and specificity? Sensitivity means what? Somebody want to give me a definition on that? I'll give you a basic one. Sensitivity means if someone is truly sick, do you detect that they are sick? I've moved away from my statistical definition before, right? It's the same thing. If someone is truly sick, does your test say that they're sick? That's sensitivity. What's specificity by the same token? If someone is not sick, does your test say that they are not sick? So you can see that in one case we're talking about the people who really are ill, can you detect them? And in the other case we're saying people who are not ill, do you detect that they are free of disease? Okay, so in the case of Ebola, we are frequently in a screening paradigm, which is to say, if someone is sick, we absolutely positively need to know. Because if somebody does have Ebola, you're going to sequester them away from people who don't have the disease in hopes of stopping its spread. Okay? So there's a huge premium in the case of Ebola. If someone's got it, you gotta know. And that means we want sensitivity high or low? High. Very high. Okay, so if you're screening for an infectious disease, you're going to put much more emphasis on sensitivity than on specificity. So now I want to talk about upside risk and downside risk. All right? What is, for this, we're going to talk about false positives and false negatives. So what is the danger of a false positive in an Ebola screening trial? If you're out in the field, you run your magic device on a person and it says they are sick, but they really aren't, what is the downside risk of that? What happens to that person? Your machine just put the finger on them and say, you're sick, you've got Ebola. If they don't have Ebola, what's going to happen?
Well, they'll get medication when they're not supposed to.
They'll probably get medication, they'll probably be isolated away from their families, they're going to be scared out of their minds, there will probably be some social stigma, blah, 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 it's a lot of stuff. But what happens, say, 2 weeks later? The hospital writes them a note of apology and sends them home saying, you never had it. Okay, so that is the downside risk. Telling someone they have a life-threatening disease when they don't is a bad thing, but it's the kind of mistake you'd rather make, because let's think about the downside risk of telling someone who does have the disease that they don't. What happens then? They go home filled with the confidence that they don't have this disease. They were just tested. This advanced machine told them, you don't have Ebola, and they're like, oh, good. Well, I guess I just have a heck of a flu. Make me some soup, right? And then now the whole family is ill, right? Terrible outcome.
Everybody dies.
What's that?
Everybody dies.
Yeah, it's a really bad way to go. We're talking about like a blockbuster Hollywood movie that has only a vaguely uplifting ending of some sort, right? Okay, so there are different risks associated with telling someone erroneously that they're sick or erroneously that they're not sick. And in the case of screening for a highly infectious disease, we put a big priority on sensitivity. That would mean that using a cutoff that lets us make a lot of false positives, but which has very few false negatives, is a priority. That's what putting that cutoff way up high and a little bit to the right means. Okay, next case, sending for surgery. All right, does everyone here still have a grandparent alive? That's great. I envy you. My grandma passed a few years back now. Being without grandparents is just kind of hard. But I want you to think about Grandpa. Anyone have a good name for Grandpa, a good nickname? What's the proper term for that? Isn't that Baba? That's like Dad? Anyway. My grandpa always went under the name Grandpa. We're a very original family. All right, so my grandpa. I think of my grandpa. Imagine that Grandpa was having difficulty peeing. This happens to a lot of older men, right? And so after months and months of this, Grandma is like, come on, would you just go to the doctor already? Finally, Grandpa goes to the doctor. And the doctor says, my goodness, you have a really high PSA level. Now, we have had a lot of problems with PSA testing in the past because people misuse the information that comes back. Because generally speaking, an oncologist who knows that somebody is at increased risk for a disease is going to respond aggressively, right? So if the oncologist believes that this gentleman who's just come in has a really high PSA level, they may say to themselves, my goodness, this gentleman has cancer, we've got to get it out. And then Grandpa goes for surgery. They clip out his prostate. I mean, it's not nice. And Grandpa is going to have lasting difficulties for the rest of his life from the surgery. So how is he going to feel if the pathologist comes back, having looked at a sample taken from his prostate, and says, "Oh, we were wrong. You didn't have prostate cancer at all." This happens a lot. This happens a lot. PSA is a really bad test for prostate cancer. It's one of the best ones we've got, but it's terrible. It's terrible. So it's frequently the case that we jump on these folks with high PSA levels, send them through a surgery, grandparented surgery. I mean, that's a big deal, right? You don't want some 80-year-old going onto the table if you can possibly avoid it. And these gentlemen then have to deal with a variety of complications that fall out of these surgeries. That's not ideal. So it might be that if you had only this test to tell you whether or not someone had cancer, that you would want to be really careful on specificity. There are many prostate cancers that are indolent. Have you heard that term, indolent? Indolent is how I feel about 1 in the afternoon after my belly's nice and full and my body says, okay, now it's time for a nap. I get indolent, right? There are some cancers that are indolent, and an indolent cancer is one that's not growing very fast. It's not metastasizing. It's not really doing much more than causing some inflammation in the prostate, right? And in many cases like that, jumping straight for surgery is the wrong thing to do, because grandpa could live for another 10 years and have that prostate cancer the whole time, and it's not going to be much bigger 10 years from now than it is today. There are some prostate cancers, on the other hand, that are just wildly aggressive, and you've got to nail those things right away. So we have this challenge then of making these judgments, and we don't make those decisions about surgery or not surgery on PSA. PSA is how you know which people to pay closer attention to. But generally, you want to have something like a biopsy to be able to decide this person's got to go to surgery now, right? Okay, so in this case, using the same curve, I've put the cutoff down here to the left. And you can see that it's very close to the left edge of that graph, which means there are very few people called cases by that rule, but almost everybody who's called a case by the test really does have the disease. Most of the time, we're looking for some sort of balance between sensitivity and specificity. And that balance is something that we really need to take contextually. We need to understand what's the downside of calling someone positive who's not, what's the downside of calling someone negative who isn't. All right. We have a mathematical strategy for doing that. It's called Youden's J. It's kind of fun to say. I always imagine, little Yoda with the ears and so on saying, Youden's J. All right, so when we compute Youden's J, we are trying to find the highest sum of sensitivity and specificity. So this is kind of a harmonic mean of the two. We're trying to take both of these factors into account. So if you really don't know how much sensitivity or specificity needs to be weighed, you can balance them together in this way. So remember that our random rule is represented by the diagonal. So we're not going to compare this curve to the baseline, but rather from the diagonal. So we have some vertical value where we sit on this curve, and we can ask how high would the diagonal be at the same x-coordinate. Then we find, basically just dropping a plumb line from the curve at that point down to the line, to the diagonal. We say, where's the place where the curve is highest above that diagonal? This is a complete balance then of sensitivity and specificity. So when we put a threshold on this, we're saying we want to achieve that degree of sensitivity and 1 minus specificity. And we ask, what is the score on our table that corresponded to this degree of separation between the two classes? Okay, so we started with a bunch of tables with plus and minus labels and values. We drew a curve from that. Now, based on this curve, we've assessed its area under the curve, and we've assessed the height of the optimal height above the diagonal to give us a rule about how to evaluate the numbers that came back from this. And now we have to go back to the table to figure out which particular score threshold applies, would yield that particular point on the curve. With that, we now have a threshold that gives us characterized sensitivity and specificity from the curve. And just like that, you've had some experience thinking about the statistics of biomarkers. I know statistics is terrifying, but I hope that the curves have a lot of value for you in understanding how we make a decision rule from the results of a biomarker survey. In this case, the ROC curve is the visualization of discrimination achieved by a measurement of a biomarker. Maybe that measurement represents one particular analyte that we were measuring by ELISA, Maybe it represents 100 transcripts that we're measuring by RNA-seq. You can do all kinds of analyses from all kinds of experiments in this context. You can even do it with soil alkalinity measurements in plants. You don't have to be doing clinical biomarkers at all for ROC analysis to be a really good way to separate out the sensitivity and specificity achieved from some measurement. Okay, when we get an AUC value, we're looking at basically how far this curve sits from a random judgment. You'll sometimes even see that expressed as a p-value, though that's not a very informative thing in a lot of cases. The p-value associated with an ROC curve is to say, is this random discrimination or not? And in almost every case, that's going to be a very low p-value. Setting a threshold requires that you have some sort of perspective or some sort of context by which to weigh the needs of sensitivity and specificity. And that is a huge part of biomarker discussions that very frequently goes undiscussed. So I'm glad we could talk about it today. Now, on next Tuesday, we're back in here. Once again, we're going to be talking about math. I know you're really excited. But this time, we're going to be talking about the fourth industrial revolution. No, we're not. We're going to be talking about the introduction to machine learning. Machine learning is one of those topics that always appears in uppercase in papers because people know that if they're doing machine learning, their work is somehow more significant than if they had left it out. This is sad, but just the same, machine learning has led to an awful lot of huge revolutions in the performance of bioinformatics tools, and I want you to be armed so that when you read a paper that used machine learning, you don't just say, oh, they used machine learning, they must be awesome, to instead say, well, no, I don't understand why they did it that way. I want you to be armed. So we're going to talk about machine learning next Tuesday, and then, of course, next Thursday, we're going to have a discussion of a paper, which means I need to get the paper from Byron Reeves sent to you so that you can be looking at that a week in advance, right? You're all going to spend your Saturday and Sunday looking over the paper, right?
Yeah.
That's so good. You guys are so awesome. All right, great. I will see you then next Tuesday. Thank you.